So now on to indefinite integrals of type 2. So these are integrals that do have finite numbers, right? So you've got a finite interval, but somehow there's a vertical asymptote involved. So you're looking at the integrand, right? I've got 1 over x squared here, which obviously goes to 0 at 0, and here 0 is on the end. So this is not going to be a function that's continuous on the closed interval from 0 to 1. It, in fact, has this asymptote. So I have to look at that, and then I have to recognize that. So this is something that I haven't been really pushing when we've been doing integrals. When we've been doing definite integrals, we've just been sort of assuming that everything's okay, that our domain of definition is okay. Now that we have these, we have to be careful whenever you have a definite integral that you're not in this kind of situation where you do have an asymptote, and that asymptote because that asymptote has to be taken care of. So I do exactly the same thing with these as I do with the infinity, right? It's just the infinite the infinite behavior is coming from a different way, right? It's not coming from an infinite interval. It's coming from sort of a singularity at a point. But I behave the same way. I just let that thing be t. So now t is going to 0, okay? And because it matters sometimes, I want to make sure where I'm going to 0. I'm actually going to 0 from the positive side here, right? Because what I've got something that looks like this, right? This is my interval. This is what I'm trying to figure out what my area is. Okay, so I'm going from the right. Sometimes it makes no difference whether it's from the right or the left in terms of actually doing the limit, but sometimes it does. So we always have to put it there just to be sure. Okay, so it's this, right? I'm going to take the integral here. Again, it's an easy one. And then I'm going to get this here, and I have minus 1 plus 1 over t. Okay? But now what's happening here with 1 over t? Obviously, as t goes to 0, this thing is going to blow up, right? Because I've got a 1 over 0, I've got infinity. So this guy, the whole thing is going to diverge. Because this goes to infinity, this integral diverges. Right? So it's exactly the same kind of procedure as we did in the other case. The only difference is recognizing where the infinity is, where you have to take the limit to, where the limit comes from, right? So that requires looking at the integrand and the limits together. You can make a picture if you want. It's not strictly necessary. Let's look at another one. Okay, for this one, again, I'm starting from 0 to 2, but my problem point is not at 0 because it's fine at 0. My problem point is at 2 because I've got 0 in the denominator at 2. Right? So I want to put here limit as t goes to 2. It's on the top side, right? So I'm going from the left, right? This is because it's my right endpoint. So 0 to t of this dx over square root of 2 minus x. Again, this integral is not hard to do. There's a little u substitution. It gets me an extra minus. But this is u to the negative 1/2. So what I end up with is u to the 1/2 with a minus, right? So I would have square root of 2 minus x, and I have a minus 2, right? When I take the derivative of that, I'm going to get this guy. And we're evaluating from 0 to t. Okay, so let's see what we have here. limit as t goes to 2 from the left, negative 2 square root of 2 minus t plus 2 of 2 minus 0. So 2, 2, 2, right? 2 minus 0 is 2. Okay, hello. All right, so now I do the limit, and this is a very easy limit, right? I just end up putting t in there. 2 minus 2 is 0. This whole part goes to 0. And then my answer remains whatever this piece was, which was 2 square root of 2. So here I got a nice convergent integral, converges to 2 root 2. Okay. So again, it's the same thing as the situation with the infinities. Some of them are going to converge, some of them are going to diverge. It's going to depend on the form of the thing that you started out with. Okay, now, in both of these examples, our asymptote was at the end of our interval. But of course, you can easily imagine a situation where the asymptote is in the middle, right? So you can, yes, that's right, that's what I wanted. So this has an asymptote at x equals 3. If I graph this function, it looks something like this. And this is my interval, right? So I've got that asymptote straight in the middle. So I have to look at it, I have to look at the integrand and say, okay, the asymptote's in the middle. What am I going to do? I have to break up the integral there. So this is actually 2 separate integrals because I have to take care of this asymptote. This is one of the things which it's tricky to recognize, okay? I mean, it's not tricky if you know that you're supposed to be looking for something like this, but, well, if you miss it, you'll get the wrong answer. I will show you that after we're done with this. Okay, so I break it up at the asymptote because then I can do my limit business. So t goes to 3 from the left. And I'm just going to use another, I'm going to use s, but I think often many people will use the same t, same letter, doesn't matter. This one goes from the right. Okay, now in both of these cases, what am I going to get? This is an easy integral, right? It's just natural log. Of natural log of x minus 3 from 1 to t plus the limit as x goes to 3, natural log of x minus 3 from s to 5. Okay, so limit as t goes to 3 of natural log of t minus 3, okay, minus natural log of 2, right, plus limit as s goes to 3 of natural log of 2 again, minus natural log of s minus 3. Okay, so you see sort of it's important, though, that these are separate integrals. They're separate integrals on separate parts of the thing here, right? So although it does sort of have something that looks similar to what we saw before, they're different because one is on the range from 0 to 1 to 3, and the other is on the range from 3 to 5. Okay? So my first one here, and I'm going to look what happens. What happens here? This guy's going to go to negative infinity. And then I'm done, basically, right? because this integral is going to infinity and there's nothing more that it can be said. I can't, so this is just going to diverge. I don't even need to deal with this one. I can deal with this one. This is also going to go to infinity because you have another natural log of 0. There is this sort of issue where, okay, this one's going to negative infinity and that one's going to positive infinity. But because the limits are separate and because these two integrals are over separate pieces, it can't do the thing that I did in a previous example where, it went underneath, right? Remember we had the natural log of something minus the natural log of something and we put them together. These two, you can't put them together because they're on totally different parts of the x-axis, right? One part is over here and the other part is over there. So don't make that mistake either. This definitely diverges. So I erased the board. I forgot to mention this last thing about this integral, which was kind of key. We showed that this guy diverged, remember, because we broke it at 3, right? We had 2 limits from the left and then from the right. And it ended up that actually both of these diverged. But if even the first one diverges, we know it diverges. The one thing I wanted to point out is, let's say you didn't realize that this integral was an improper integral, that it had that x equals 3 asymptote in the middle. Well, you can just go down here. If you're not paying attention, evaluate it like this. From 1 to 5, I've got natural log of 2 minus, so it turns out natural log of 2, right? So again, and I get an answer of 0. Well, it's not 0 because it's infinity, right? It diverges. So you have to be careful. This would be the wrong answer. This doesn't work precisely because this integrand is not continuous over the whole region from 1 to 5, right? It's got an asymptote. So you just have to be careful. From now on, you're going to have to watch for that. You don't have to worry about it when there's not limits. When it's an indefinite integral, we just assume that this thing was over the largest possible domain of definition. So fine, we're just doing antiderivatives. But when there is a region, when you have a specific interval, you have to make sure that your integral is continuous on that region, that you don't have this asymptote business, okay? Even if it was discontinuous and it was finite, you'd have to do something, right? We've seen examples, plenty of examples with, piecewise defined functions where you have to break it up, right? Because the domain changes, the definition changes. That's another example where the function is discontinuous. So if the function is discontinuous at a point, you have to break the integral up there. That's the same thing here. The only difference is that the point that we're breaking it up is actually an infinite discontinuity. That asymptote is going to mess the whole thing up. Now we're in this situation where we have to do limits and stuff.